we'll begin. Heavenly Father, we thank you for this day again, Lord. I thank you for the students and for this time we have just to study your creation. Pray that we be able to use this time wisely and that you be glorified in what we do, Lord. In your name I pray. Amen. All right. Let us go through the list of grievances. No, I'm sorry, the solutions. So you got to use your imagination to figure out what the problem statement is here. Clearly, I need to give you guys more strong wording, strong encouragement. Like, there's a sentence at the start of all these problems which says little things like calculate the partial derivative or find the tangent plane or whatever those instructions are. Like, we need to write those on the board to make this productive, right? Oh well, 20 minutes too late. Sorry. To the rest of you. So this one is use the chain rule to calculate the partial derivatives, express the answer in terms of independent variables. So in this case, the independent variables are s and r, all right? We're given that f of x, y, z is xy plus z squared, all right? And so let's see here. What did you do? X partial y partial s plus y partial x partial s plus 2z partial z partial s. This would be, and so, okay, but yeah, but this is equal to that, right? And then so partial f, so you figured out that this is 0, very good, right, because of this. And the partial derivative of y with respect to s is what? It's just r, well, 2r, right? And the partial derivative of x with respect to s is 2s, so we've got, looks like 2xr plus 2s, 2ys, right? And then a similar calculation, we'll calculate the partial derivative of f with respect to r. Again, the chain rule, partial f, partial x, dx dt, partial f, partial y. Now, I gotta complain a little bit here. We should be writing partial f. I mean, the x is fine, all right? I mean, that is fine. So we got partial f, partial x, partial r, partial f, partial y, partial r, right? Partial f, partial z, partial r. And I think that this is that, and I believe that that is that, and I believe that this is this, and that's fine, all right? Good. And I respect that you did it in your head. It's okay, right? It's okay. I think those are right. Yeah. But there's something that's not quite on the level here. This notation isn't quite right. Like, we should be writing partial z, partial t here, all right? We reserve notation like ddt for a problem that's more like this one. See, this one here, the ultimate differentiation is with respect to a function of time alone. There's only one independent variable here, so that we're calculating a total derivative. We use the partial notation when there's 2 or more independent variables, like in problem 1. Oh, by the way, it was pointed out to me problem 6 is the same. Do we agree? 2sy plus 2xr. See, when I looked at this first, I thought this was a 6, but now that I've been educated by problem 1, I clearly understand that this is an r, right? So, and likewise, 2sx plus, okay, 4zr. All right. Sorry, I'll try to behave myself. I've done nothing but write on whiteboards most of my adult life. That's not true. The starting of my adult life, I wrote on this thing called Chalkboards, the magical devices that provide positive friction as you draw the writing utensil across the surface. It's amazing. You can do this thing called shading. It's, you know what I'm talking about. Like, I don't know what do we call that. I mean, it's just nice. Fine.
Tactile feedback.
Tactile feedback. There we go. I don't know. Positive friction seems like something I just made it up, but you got me. Thank you, John. Appreciate that. Remember that later. No, I'm not petty like that. You're safe. let's see. Oh, yes. Problem 3. But anyway, chalkboards. There are no chalkboards here. Oh, yeah, problem 2. I guess I shouldn't skip that one. This was yours, wasn't it? So we were supposed to find, hey, check it out. This is the instructions, right? That's pretty much it. Calculate the second y derivative of f at the point 2, 3. So what did he do? He found the partial derivative of this with respect to y, and then the second, and then differentiated with respect to y again, which, let's see if I believe it. I believe it, but you guys got to be lazier. Check it out. F of xy is 2xy log y, right? Actually, is that lazier? Maybe that's not lazier. Maybe leaving it y squared is lazier because I don't have to do product rule for y. I retract my algebraic comment. I will retract my algebraic snobbery. There we go. It's gone. This was nice. I take it back. So 2yx over y squared, I think I believe that because chain rule brings me 2y. 1 over y squared, so we got log y. Then, oh, but let's just take a step here. This is 2x over y squared, right? Over y, rather. Right? Which I think you believe anyway, because you wrote, no? Oh. Well, so you just differentiated that without doing the algebra, which makes more work for you, but you might still be right. 2x, that's the derivative of the top. But, remember when you have f over g prime? How's it go? F prime g minus fg prime over g squared, right? But the point is that this g here is a non-negotiable. So you're missing something right there. What are you missing? Y squared, yeah. So that's gonna ruin what follows. So sorry, but the idea was right here. Just there's a mistake in the quotient rule. The idea of plugging in the point looks good to me. Let me fix it. Won't take long. So what's fyy? Minus 2x over y squared, right? So fyy at the point 2, 3 is minus 2 times 2 over 3 squared, otherwise known as minus 4/9. See, there you go. Any questions? You guys break in if you have questions. Problem 3, the question was to find the equation of the tangent plane of the given function. So the function that was given was f of xy log of 4x squared minus y squared. The point where we want to find the equation of the tangent plane is 1, 1. You guys might remember this is the third and final, I presented to you that day how to find the tangent plane to a level surface, to a parametrized surface, and then finally at the very end of class I stated how to find the equation for the tangent plane to a graph. So this is one of those. And the way to do that is you basically just take the value of the function at the point, you calculate the gradient, you take the dot product with the displacement vector from the point to your variable xy, and that gives us the equation for the tangent plane. That's the best linear approximation. Okay, fine, a fine approximation to the graph near the point. So for this function, she took the gradient, yay, partial differentiation, plugged in the point, we get 8/3, 2/3, and then we just have to go to what is the tangent plane? How do we define? In fact, this is the definition for the tangent plane to a graph, right there. This right here, this is in fact the definition of tangent plane to graph at the point 1, 1 for that function. All right. Should I let you guys have a 3x5 card for the next test? Yeah. Oh, I should. Okay. So maybe this is one of those things that ought to be on there, right? Like if I have a graph, the equation for the tangent plane is found in this way, right? If I were you, I would have clearly marked down how to do the tangent plane for a graph, for a level surface, and what else? Yeah, parametrized surface. Those are our three flavor options, yes? Zoop.
2y not being negative.
Uh-oh.
The gradient.
Uh-oh. 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 Yep. So I will take that sign correction and add it. Minus I mean, if you write red, you have to correct in green, right? Minus. I wrote it symbolically, so nothing to correct. Minus. And last but not least, e's minus. Yeah. Thank you. And so there you go. This is the equation of the plane, which best approximates z equals, the log of 4x squared minus y squared near the point 1, 1, natural log of 3 in 3 dimensions. Yeah. The equation for the tangent plane, just a gut check if you're doing things right or wrong. Remember, the equation for a tangent plane should be a plane equation, right? Which means that it involves z, x, and y, and numbers multiplying them. If you've got an x squared, or a y squared, or a z cubed, or a natural log of whatever, sine of whatever, exponential of whatever, and if those whatevers are variables, that is not a plane equation, right? And that means you have failed to do a very important thing, which is to evaluate the gradient, or the derivatives, or whatever it is you're working with at the point in question, which is a necessary and important part of finding the tangent equation to the tangent of a graph. In the last test, a lot of you made the mistake when you're finding the tangent line, you differentiated the path, and then you failed to plug in the time of tangency, right? You just gave me like the parameterization of the tangent line, which had all kinds of very non-linear, curvy functions in it. This is, a very popular standard mistake. It continues to be popular, even in this class. And you guys are better, much better than most, as a class, I believe. I would not be at all surprised if I end up giving like 30, 40% A's in here if trends continue. Not giving, you guys will earn them if things continue. Okay, so where was I? Oh yes, so we're supposed to calculate partial derivative using implicit differentiation. So if this is it, if this is the universe of discourse, like this is all that we know about x, y, z, and w, what are we to conclude here? If you're to calculate partial w, partial z, what are the independent variables? So this altogether, that tells me that w should be viewed as a function of x, y, and z. W is my dependent variable, x, y, and z are independent variables. Okay, and that governs everything we do past that point. Okay? So I was encouraging Grant to make life easier and do algebra before we differentiated, so we decided to group this and that to put the w out here like that, right? Because that way we only have to do one product rule. If we just differentiate this like just straight, you get 2 product rules, right? Less awesome. So one product rule, partial w, partial x times that, right? Plus w times the partial derivative of that with respect to x. But the z squared differentiates to 0 because z is independent from x in this context. And so we get w times 2x plus 0. And then this 3w squared partial w partial x because of the chain rule. Remember, w is a function of x. And then at that point, we got to isolate partial w partial x. So we do a little bit of algebra. And then just divide by the coefficient. And there you go. Yep.
We're asked for partial w, partial z.
No! Maybe this is why Grant was confused by my advice. Yeah, you should be. All right, well, we fixed it. Yeah, sorry about that. You're not allowed to do that. Use the chain rule to calculate the total derivative of this function of x and y composed with this space curve in the plane. T maps to C of t. C of t is a vector in the plane, right? So this is a path in 2 dimensions. We're evaluating a path at a function of 2 variables. In total, we get a function from the reals to the reals. So the chain rule for this guy is the gradient of f times dc dt, right? If you want me to write it out in less elegant notation, this could be, maybe this would be the way you guys would think about it sometimes. It's partial f partial x times dx dt plus partial f partial y times dy dt. That's what this is, where I'm thinking of c as being x of t comma y of t. right? But in any event, the gradient of f is 1 minus y, comma minus x, right? And then what's the derivative of the path? Well, it's 2t minus 4, right? That's the velocity vector to c. And we take the dot product of those. This bar means we got to plug in x equals to t squared. We got to plug in y equals to t squared minus 4t here because that's the chain rule, right? Derivative of the outside function times the evaluated the inside function, right? And so that gives us this dotted with that. Fine. And it's my, I mean, I cramped his style here. So 2t minus 4 with my big bar writing. And I'm just going to rewrite what you wrote down there again because I don't want to make her zoom the camera in. Here's 2t minus 4, is that right? I think I've interpreted what you wrote. I mean, that's what you wrote. Anyway, does it, yeah? But it's minus 4t up here.
Well, it's 1 minus y. The y was t squared minus 4t.
Ah, yes, thank you. Right, he's right. Because it's minus y, the minus makes that into a, whoa. 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 Oh, excuse me, I'm confusing. I gotta be, this is the main mistake we'll make here. If we're not careful, we'll confuse the derivative with the function. And rather than trying to assign blame, let me just work it carefully in writing that we can all see. Yeah? So I'm going to scratch that because I know there's an error in there. Sorry. All right, so we've got 1 minus y minus x dotted with dc dt, right? Which is what? 2t minus 4, right? But this, of course, is, I mean, with the understanding that that should be what? 1 minus y. What is y equal to? T squared minus 4t. Parentheses are our friend, right? Minus x, which is minus t squared. Still got to take the dot product with the 2t and the 2t minus 4. So we got 1 minus t squared plus 4t. You got your wish. Minus t squared dotted with 2t minus 4, which may, in fact, be what was written there before. I can't remember. And all right, so 2t times, oh, good grief, not a vector. Dot product a vector? Not if you want to pass this class. All right, 2t, 1 minus t squared plus 4t. It's true. If I see somebody write a dot product as a vector at the end, I look for ways to fail you. I'll admit it. It's true. It's just, there's certain things that offend Calculus 3 professors, like confusing vectors and scalars in a way which I cannot ignore. Everyone will do it. The best student will do it in here somewhere by accident. It's when it's done intentionally, and then that leads to errors. It makes me angry. So anyway, but yeah, whatever. I know. Maybe I should get counseling. I don't know, but there you go. I mean, we could simplify that, but there it is. Does that make sense? Yeah. I should have not left this pink marker up here. Oh, we already talked about that one. Good. So, problem 7, we were supposed to calculate what? The second partial derivative with respect to x of f, and also the second partial derivative with respect to y of f. And do we all agree? Differentiate with respect to x 2 times, what do we get? The first drops us down to 6yx minus 6y to the fourth. The second derivative with respect to x kills off the second piece and just leaves us 6y. Very good. And the second partial derivative with respect to y, well, the first one does what? It drops us down to 3x squared minus 24xy cubed. The second derivative with respect to y kills off the 3x term and leaves us with 3 times 74, which is 3 times 24, which is 72, xy squared, and there you go. The people who were working other problems on the board seeing this problem, you feel a sense of inequity, right? You feel like it's not right that someone should have that problem and earn 10 points, and yet I should have that problem and earn 10 points. It's not right, right? Life isn't fair, though, right?
That's your way of teaching us lessons.
That's right. It's one of life's lessons. Life isn't fair. Anyone who says differently is selling you something. Let's see here. That's a quote from somewhere. Where is that from?
Princess Bride.
Is it a Princess Bride quote? Seems right. Seems right. To quote my community college professor, this dog will not hunt. Es no bueno. This is, in fact, I mean, I understand in your heart you're thinking that's the derivative, and some mathematicians would even use that notation, but for us in here, we insist on writing gradient of g for that, okay? That's the gradient of g, but, yeah. And, all right, so who had that? Spencer.
Just to find a tangent equation, and I had no idea how to do that, so I just made something up.
Okay. Now that makes sense.
Now I know how to do it.
Now you know how to do it. All right. So very good. So now you know how to do it. Now that you have seen the other problem that's kind of like it, and that's good. So we just calculate the gradient of g at the point 2, 1, which is what? E to the what? E to the e squared, right? And then that's minus 4e squared, right?
Wait, that's already the gradient.
Yeah.
Oh, sorry. Never mind. I thought you were symbolically differentiating again. My fault.
Okay. Carrying on. Thus, z equal to, these don't have to be complicated, guys. So that's part of the reason we do these, is so that maybe it removes some of the mystery. Finding equations to tangent planes are easy if you know what you're doing. You just have to calculate the gradient, plug in the point, and construct the linearization for a graph, right? Again, if it's a level surface or if it's a parameterization, we go down a different path, logically, but here's how we do it for a graph. What's g of 2, 1? E to the 2, also known as e squared. Let's see here. So we got ourselves e squared. I should have factored out that e squared. Oh well, too late. So we get e squared. I'm factoring out that e squared. 1 plus 1 times x. Oh, fine, I won't factor out the e squared. I'm feeling bad about it now. I have trouble making decisions. Well, there's an e squared. There's e squared everywhere. I could just factor the stupid thing out to the front, but I'm going to write it 3 times in the interest of not confusing you. I will begrudgingly give you an extra step. And I'm feeling guilty about not simplifying it, so I'm going to simplify it. This is e squared times what? X minus 4y, yeah? Yeah, minus 5. So since it wasn't too much trouble, and I felt like it, I simplified it. But honestly, folks, if you write this down, you could leave that as the answer. I'm fine with that, okay? The point here is less about simplifying. It's much more about, do you understand context and application of ideas, right? Partial differentiation is just the first thing. There's so much more after that. All right, so problems 9 and 10 are an old foe that maybe you have not conquered yet, the directional derivative. All right? The directional derivative is easy if you know what you're doing, and I bet you guys did. So inverse tangent x over y, the gradient is y over 1 plus xy squared. I think I agree with that. X over 1 plus xy squared. Yep. You're supposed to find the directional derivative in the v direction at p, right? It's a trap. It's a trap. See, because v is not a unit vector, right? But you saw through it. You made your v hat. Yay. unit vector. That's what we need. So the directional derivative, we calculate the dot product of the gradient with the unit vector in the direction at the point. So plugging in the 0.34 gives me 4 over 145 and 3 over 145. I took the dot product with v hat, and I get 4 over 145 times root 2, 3 plus 3 over 145 times root 2, which gives me 7 over 145 times the square root of 2. Woo-hoo. Very good. Very nice. The only thing missing here is perhaps the notation, which is that the directional derivative in the v hat direction of f, right, at the point P was equal to the gradient. I mean, I'm not saying this is missing. I'm just saying, remember that what they're doing is using this formula, right? This formula is the basis of everything. The directional derivative is the gradient evaluated at the point dotted with the unit vector direction we're interested in. Over here, we have yet another directional derivative. I feel like you got the better deal on the gradient calculation for this one, right? Compared to the last one, right? I mean, polynomials, nice. So 2xy cubed, 3x squared y squared, partially differentiating this with respect to x, with respect to y, gradient. Plug in the point in interest, minus 2, 1 into the gradient. That gives me 2 times minus 2, which is minus 4, 1 cubed, which is 1, minus 4. Good. Just going to, there we go. Minus 4, and then 12. 3 times 4 is 12. Very good. And then this, well, this is right, but it's also wrong in the sense that you should do something like say, okay, so the directional derivative in the v hat direction of f, at the point P is equal to this. Maybe even better. Well, this is fine. This is fine. You've already done the work up here to lead to that, and then I would just like to see some kind of like that or something. We try not to put floating expressions, but I'm just quibbling. Yeah. I have a good feeling about the test upcoming. I think you guys may be getting close to where you need to be. I bet a lot of you still have a lot of work to do on the chain rule, though, right? Yeah. There's some subtle issues there. All right, so we got that done with. Let's finally. Oh my goodness, that took long enough, didn't it? Oh. But I do think it is a wise use of our time. I really do. As much as I hate it. I guess I should skip the part where I tell you I hate it. Well, eventually I'll learn. So let's talk about how to calculate gradients in other coordinate systems other than x and y and z, or x and y. So start out with the plane. Start out with R2. What's the gradient in Cartesian coordinates in R2? What was our definition of the gradient in Cartesian coordinates in R2? It was what? Gradient of f is what? Partial f partial x, comma, partial f partial y. But really, what's going on there, it's more than just that. If you rewrite that in terms of x hat and y hat, you can see more clearly what really the definition is. I mean, that's not wrong, what I just said. It's just that we really need to write it in terms of x hat and y hat to fully appreciate how to change it from the Cartesian coordinate system to another coordinate system. So R2, right, we have a function that goes from R2 to R, right? We can calculate the gradient of f. How does it work? Like I just said, partial f, partial x, partial f, partial y, right? But that is also equal to x hat, partial f, partial x, plus y hat, partial f, partial y, right? Now, how do you guys remember? I want to convert this to polar coordinates. So polar coordinates, what do I get to work with? Differentially, I get to work with partial partial r and partial theta, right? But what else is in polar coordinates? Also the polar frame, the r hat, the theta hat. I have to build vectors with the r hat and the theta hat. That's the way way the game is played. Because we're talking about vector fields. The gradient is a vector field. It's an attachment to a vector at each point in the plane. So to properly describe the gradient vector field with polar coordinates, I also need to pay attention to the polar frame to do it properly. So I need to convert the derivative and the x hat and the y hat. Can you guys remember what r hat and theta hat, what were these? Remember, it was cosine theta, sine theta, like this, right? And theta hat was what? Right. Can you guys tell me how to write those in terms of x hat and y hat? Well, but these in terms of x hat and y hat, it's like cosine theta, x hat, right, plus sine theta, y hat. And what's this one? Minus sine theta, x hat, plus cosine theta, y hat, right? All right, fine. What would x hat be? Check this out. Here's the trick. If I want to write x hat in terms of, r hat and theta hat, how do I do it? Check this out. What I do is just use x hat dot r hat plus x hat dot theta hat. That makes sense because we can use the r hat theta hat basis to decompose a vector. And since r hat and theta hat are perpendicular, this will give me the projections into the r hat direction and the theta hat direction. What is x hat dot r hat, though?
Looks like our hat is just cosine theta 0, 0.
Well, how would you calculate x hat dot r hat, this one? How about, here's r hat right here, right? What's x hat? 1, 0. What's the dot product of those? Cosine theta, right? What's x hat dot theta hat? Minus sine theta, right? Theta hat. What's y hat then? Same kind of calculation, right? Y hat dot r hat. R hat plus y hat dot theta hat. Theta hat. What is y hat dot r hat, though? That's sine theta, right? What's y hat dot theta hat? Plus cosine theta, right? All right, great. So we got half the battle done. Partial f, the gradient of f is apparently, well, it's x hat, partial x, right? Plus y hat, partial f, partial y. What is x hat? It is cosine theta, r hat, minus sine theta, theta hat, right? And then by the way, what is partial f, partial x? What did we do last time? While you're thinking about that, what's y hat? Y hat was sine theta, r hat, minus plus cosine theta, yeah. Cosine theta hat, like so. Can you tell me how to rewrite partial f, partial x in terms of r theta derivatives? Remember, we worked this out last class. What was it? And how about partial f, partial y? Yay! There you go. That's the gradient in polar coordinates. We've eliminated the x and y. All that remains, x's, r's, r hats, and theta hats. That's the polar expression for the gradient. Fortunately, this simplifies. Otherwise, I wouldn't be talking about it. Right? This collapses down a lot. See what happens? Cosine and cosine, and sine give me r hat, partial f, partial r. Because we get sine squared plus cosine squared times partial f, partial r times r hat. And that just leaves us r hat, partial f, partial r. And then how about the thetas? Well, we've got, partial f, partial theta with a sine theta, right? That gives me a sine squared theta over r, partial f, partial theta, right? And over here, I get a cosine squared theta over r, partial f, partial theta, theta hat. So you put all that together, that gives me a 1 over r theta hat, partial f, partial theta. And what else is there? Cross terms, right? Things like this times this, which cancels with what? This term over here, right? Those are natural enemies. And likewise, if you look at this guy times that guy, it's going to cancel with these guys. Minus, plus, all the terms the same. There you go. So this is the formula. The gradient in polar coordinates, what could be simpler? It's r hat partial f partial r plus theta hat 1 over r partial f partial theta. So that is the formula for the gradient in polar coordinates. This is really nice because then here, like, how do you use it? So basically your homework question is not, I don't think your homework question is to derive them, is it? It's to use them, isn't it? I think I said use the formulas which are given in my notes to calculate these gradients, right? No? Did I ask for more? Uh-oh, I broke Nathaniel's brain.
Not really, no. Just find f such the gradient of f equals that.
Oh, yes, that's a little bit different. So something like that would be, how about this? So I could try something like r hat plus theta squared over r theta hat equals to the gradient of what f? That would be an analogous question to the one you're pointing at. 56b?
But for 56b, we would need to derive the gradient in terms of spherical.
Yeah, I will write down the spherical gradient soon. Let's stay in the polar world for just a second here. So if you wanted to find f that was the gradient, so the gradient some f such that the gradient of it matched this polar vector field, what would you have to do? You go back to the formula we just derived, right? And we have to match components, right? This has to be equal to that, and this has to be equal to that, right? So you'd have to solve partial f, partial r equal to r, and what else? Partial f, partial theta equal to, notice the 1 over r's cancel? Yeah? That was on purpose. So partial theta squared. So what can we use for f? So for my made-up problem, there you go. That's a function which picks up, r hat plus theta squared over r theta hat as its gradient vector, as its gradient field. But Nathaniel's right. The one I asked you about was for the evil spherical case. which is uglier still. Before we get to the spherical, though, what's the gradient for cylindrical coordinates look like? What if I have f of x? What if I have f of like r, theta, and z? What's the gradient of f in that context? Well, r and theta satisfy all the same stupid formulas that we've just been talking about in the plane. We're just tacking on a z. So the gradient for cylindrical coordinates, by all the calculations we've done and a few that we haven't, that are kind of trivial, r hat partial f partial r plus theta hat. You know, I don't like to write it this way. Partial f partial r, r hat, plus 1 over r, partial f partial theta, this feels better, theta hat. And then finally, what goes last? If I erase this 2 and put a 3 here, what changes? We just add this term, right? Plus the z hat partial f partial z. That's the gradient in 3 dimensions for a function of 3 variables. So the same calculation to go through. We just also have a partial f partial z hat term here. That's the gradient in cylindrical coordinates. In spherical coordinates, some weird stuff happens. Before I show you the weird stuff, any questions? Because I need to project the weird stuff. Because otherwise it will take me all of the remaining time just to work out the formula, and that won't serve any of us, because I've showed you the basic idea that you need to derive these formulas, and maybe some of you don't care about deriving them, right? You just want to use them. You know, most of you are engineers, and that's not an entirely wrong idea to have. I mean, I want more for you. I want you to understand where things come from. But I understand sometimes you just have to pick up a tool off the shelf and use it, right? So we're going to kind of engage in that mode of thinking here for the spherical case. That's not entirely true. I'm going to show you some of the manufacturing process for making the spherical gradient. And I'm also going to live dangerously. We'll see if my computer will not turn itself off in the time it takes to project this. Welcome to. No. I've done enough time traveling lately. Let's see here. At least yours has a. What was your battery life?
About 9 hours.
Yeah, so it's about like 8 hours and 50 minutes longer than mine. Oh, fine. It's going to be annoying when it turns off in like 30 seconds. There we go. So guys, the section in the notes where I talk about the gradient in non-Cartesian variables, it's at the very end of the chapter. It's the last section. It's basically page 220 to 221, 222. And so I start out by just working. We actually just worked through this stuff more or less. I took a different approach in the notes in terms of solving for r hat. I mean, I looked at this as 2 equations and 2 unknowns, and I solved for x hat and y hat in terms of r hat using 2x2 matrix stuff. But whatever. Anyway, the point is we get the same gradient we just derived, and then there's the cylindrical one, great, and spherical. Woo! Spherical coordinates. So spherical coordinates, you're trying to take the partial f partial x, x hat, partial f partial y, y hat, partial f partial z, z hat, and convert it all into partial derivatives with respect to the rho, the phi, and the theta spherical coordinates, as well as the spherical basis, the spherical frame, your rho hat, your phi hat, your theta hat, the vectors which point in direction. By the way, guys, I don't think I've emphasized this enough in here. The reason we care about spherical coordinates and things, maybe some of you guys are taking, are you guys taking like physics 232 right now? Right? Here's what the Coulomb field looks like. Coulomb field in XYZ coordinates. What does it look like? It's, how's it go? Q over 4 pi epsilon naught, right? And then you could write it x squared plus y squared plus z squared to the 3/2 power times the vector xyz, right? You could write it like that. Or you could write that as q over 4 pi epsilon naught. This is the r vector over r cubed. So that's q over 4 pi epsilon naught r hat over r squared. Now in here, we write q rho hat over 4 pi epsilon naught rho squared. But which is a better way of expressing what the Coulomb field is, which is a spherically radial field which drops off as the square of as reciprocal to its distance from where the charge is. Here I've put the charge at the origin. I mean, this formula is fantastic because when you write the magnitude times the unit vector, whatever the coefficient is the magnitude. Magnitude q over 4 pi epsilon naught rho squared. That's the Coulomb field magnitude, right? And it points in the spherically outward direction. As compared to what you face in Cartesian coordinates, yucky, right? So Cartesian, bad. Spherical, good. Bad, good, bad, good. All right. Brainwashing complete. Anyway, to actually work out the gradient for an arbitrary function, we actually have to find these terms. And the spherical frame, it looks like this. And so, yeah, after about a page of calculations, it simplifies down pretty nicely, and we get this formula. So this is the gradient in math spherical coordinates. Rho hat, partial f, partial rho. Phi hat, partial 1 over rho, partial f, partial phi. And then theta hat, 1 over rho sine phi, partial f, partial theta. Now this makes so much sense if you think about the interplay between spherical and cylindrical coordinates. What is r in cylindrical coordinates versus spherical coordinates? Do you guys remember? We draw the picture. We have the point. We drop the thing down to the xy plane. This is theta. This is phi, right? What's r? This is rho. This is rho sine phi. It's also r. Right? So really, this is not surprising that the piece of the gradient corresponding to theta is 1 over r partial f partial theta. It's just that now I've written it in spherical coordinates, so the r becomes rho sine theta, rho sine phi. Now this over here, weird and new, but there it is. So questions? Do you have a sense of how to start the homework problem now? I mean, what you want to do is set what you're given equal to that, right, and try to solve the partial derivatives that you face. Let me do a stupid one. So was 64b we're talking about? 56b. So what if I had gradient of f was like rho hat plus 2 over rho phi hat plus 3 over rho sine phi theta hat, right? This is very dumb in the sense that we just worked out that that's, partial f, partial rho hat. I say we worked it out. That's kind of a lie. 2 over rho. We looked at how we work it out. Partial f, partial phi hat. 1 over rho sine phi, partial f, partial theta hat. So for these two things to be equal, the components have to match, right? So this has to match that. This has to match that. This has to match that. So what's that give me? I get partial f, partial rho equal to 1. Partial f, partial phi equal to what? Yeah, 2. partial f partial theta equal to 3. Now, I think your problem is slightly more exciting than that. I think you actually have functions rather than just 1, 2, 3. But with 1, 2, 3, those are easy to solve. We just integrate them, right? Like integrating this suggests f is equal to rho. This gives me plus a 2 phi. This suggests plus 3 theta plus a constant. There you go. That kind of f will pick up my given spherical vector field as its gradient field. So you guys have questions about other homework problems? I can try to load it up here.
57.
We have mission 4?
Yep.
Ah, yes. So, all right. Maybe, I'm trying to think about the right way to talk to you guys about this without just solving it. Yeah.
Just solve it. Solve one of them and we can do the other two.
I'll do it for n equals to 3. How about that? N equals to 3. But you need to do it for n. N equals to 3. R is the square root of x squared plus y squared plus z squared, right? So the gradient of r is what? X over r, y over r, z over r. We've been through this song and dance before. When we calculated the gradient of rho, these partial derivatives were done. So here's the thing. That is actually, the gradient of r is what? It's actually 1 over r times x, y, z. And in this notation, in this problem, I suggest that that be denoted r vector. So what happens here? We've got 1 over r times r vector. That's also known as r hat, right? So let's put that in the bank. By the way, you should be able to prove the same in Rn. You don't just have 3 things, you have n things, but the same pattern holds in the calculation. Just so we're clear, what's the gradient look like in n dimensions? What is it? Partial f, partial x1, right? Partial f, partial x2. Partial f, partial xn, right? All right. Part B. You're supposed to calculate the gradient of what? R squared, right? The hint. What is the point of the hint? The point of this hint is to encourage you that when you're faced with the gradient of the square of some function that you already know the gradient of, there's a chain rule. The chain rule says that that's twice the function, right? That's the derivative of the outside function, the squaring function, times the gradient of the inside function, which is what? 2r hat, otherwise known as 2r. So you don't like that. You're like, I don't like that. That's not a good way to do it. How about this? R squared is r dot r, right? What happens when you calculate the gradient of r dot r? You could prove that, well, let me shut up. I don't have so much time. I have other thoughts. They don't matter. Do you understand the hint now? The point is, if you think through the hint, I mean, of course, for part B, you're also, if the hint is just not clicking for you, you could just write down r squared and calculate the gradient directly. It's fine. But if you do so, please try to simplify your answer so that you see what it truly is, which is twice the radius vector, right? What's the gradient of 1 over r? Well, there, again, chain rule, right? The gradient of 1 over r is minus 1 over r squared times gradient r, right? This is actually very interesting because this says that the gradient, for example, in 3 dimensions, the gradient of 1 over the spherical radius, right? It's equal to minus 1 over the spherical radius squared times rho hat, right? So this pretty much tells you that this function, 1 over rho, gradient vector field is the what? Up to a sign, it's the Coulomb field. See, the Coulomb field is rho hat over rho squared. This says that if you calculate the gradient of 1 over rho, you get rho hat over rho squared. And well, there's also a minus, but it's kind of neat. In physics 232, that minus gets wrapped up in the definition. The electric field is minus the gradient of the voltage function, right? So if you set the voltage function to be 1 over the rho, then you get minus the gradient of 1 over rho, which is, by the way, rho hat over rho squared. If you guys are not taking physics 232, you may ignore my remarks for the moment. Thanks.